All right, guys, I think we can start now. So welcome to our review session for the final exam. We'll try to talk and solve more problems which are relevant to your final exam. But also, let me mention something just this is the review session. The final exam.
It's a take-home final exam.
Yes, will be a take-home final exam. So take home 24 hours final exam. So the exam will be sent. So that will be. So I will send it tomorrow at midnight. So basically at 11:59. Wait, what's going on? Just a second. Share content. Okay, sorry about that. I forgot to share the content. Okay, so I hope it's recording too. Anyway, so like I said, it will be a 24 hours exam. So it will be sent to you tomorrow at midnight. So from Friday to Saturday, maybe I'll send it a bit earlier, a couple of minutes earlier, and you'll have 24 hours to send it to me. And the way you're gonna send it to me, you'll send it as a PDF file. You'll create one PDF file, and that PDF file will contain your name, right? And the class's name, Math 4 351 Advanced Calc 2.
Sorry, just to clarify, sir. So if it's getting sent tomorrow at midnight, does that mean we have all day Saturday to turn it in by Saturday at midnight?
Okay. Yes, exactly.
All right. Thank you.
Another thing, do you still want the LaTeX file to be?
Yeah, that I was about to talk about this. Also, those of you who wanna, so you can send it as a PDF file, but also you have another option. You can write the final in LaTeX. The final, I will send you the final in LaTeX via Overleaf, and you can share the file with me via Overleaf. Make sure you create a very different file from all the others, from the homework and everything. The final will be called final exam, your name and final exam for anyway for Math 4351. So in LaTeX via Overleaf. So the file's name you'll share it with me, just like you shared the homework assignment so far, and you'll put your name, final exam, or final exam, your name, Advanced Calc 2, Math 4, just like 4351 Advanced Calc 2, Calculus 2. Those of you who do this, I will award 3% extra. Award 3% extra credit to your final exam.
Will you send us the coding if we do it on?
Yes, yes, absolutely. The code, when you will receive my email, you will also get the code as well. So you will see my email with the, I'll post the exam, the PDF file on my website, and I will give you the link to that. And also, you will also receive the code. And you just, like you have been used so far with the homework, you'll enter your solutions there. Those of you who, yes.
The project is due tomorrow, right?
Yes, the projects are due tomorrow.
Okay.
Okay. Do you have any other questions regarding the final exam? Like about the setup or anything? So like I said, 24 hours, and I want to say one more thing. You will not post any of this on check, anyone who posts anything on check will have his final voided, will be void, and therefore the person who does this will fail the class. So I hope I make myself very, very clear. Also, you're not allowed to talk to each other, not at all. Anyone who does this, again, will fail the class. So you're on your own. You can look for anything you want on the internet, theorems, or you can look at the notes. The exam will not be the most horrible thing you have ever experienced. It will be just like any other exam. But the only thing I want to, what I want from you is your code of honor, that you did the exam on your own. And this is very, very important. So I hope I will not be put in any situation where I have to go and do an investigation about who posted this, and then I have to go to the university level and so on. Please don't put me through this. I think I have been generous enough with the extra credit, with homeworks and everything, with grading, so that you wouldn't have to go this route. Okay. With that being said, I want to, do you have any questions about the final exam? But there will be 5 problems. Very nice problems. I'm sure you'll love them. Like I said, they're not going to be like the most difficult problems you'll ever see in your life. No, not even close. If you understood the material and if you know where to look for, you're definitely going to do them. It will not deviate too much from the homework problems. In fact, I would say that some of them are even easier than the homework problems. So the homework problems were a little bit difficult, but I think that's the way homework problems should be, more difficult than the actual exams. So there'll be 5 problems, 8% each problem. So in total, you'll have 40%, just like your 40%. There will be no extra credit problems. The only thing extra credit is that 3% if you write the exam via overleaf. Like I said, please write with as many details as possible. You have to write neatly. You have to provide as many details as possible. I think there is enough time for you in 24 hours for 5 problems for you to provide as many details as possible. I want this to be very, very clear. I want to see that you actually understood what's going on there in that problem. And I won't be forced to deduct any points if you're missing some arguments and so on.
Also, about the total grades, what's the standard for an A and B and C and so on?
Say that again.
What's a grading standard for letter grades?
For the standard for each problem, grading each problem?
No, I mean like for the total grade for the letter.
For the total. So this is 40% of your total grade. So basically I will just add everything up and then we'll see. But I think with so much extra credit at this point, I'm trying not to do everything that I can so that not many people fail this class.
So with like 90% still an A, or like are you?
Yes, exactly. The grading scheme will be the classical one. 90%, over 90% will be an A. Then, well, it depends. Probably at 90% or 88 to 89 will be an A minus or something like this. I'll decide over the grade. Depends on how many points you'll have, and we'll see. But I think with total and everything, I think you can go over more than 135 or maybe even 140. So.
Hey, Cezar. So in the first class we had, you said for the final exam, after there's like a window where we can argue different corrections. Would that still apply now or not?
Yes, of course. So those of you who, so the final exams will be graded the next day. Hopefully, I'm going to finish grading all of them in one day. I will post the notes on the Blackboard. And then after you see your grade on the Blackboard, if you feel that you deserve more, we can have a chat. You can send me an email, say like, hey, I want to talk about the exam. And now, just like I did with some of you, and I will send you the grading scheme, how much I awarded for each problem. And then if you feel like um, you deserve more, then we can have a chat and we'll discuss whether you actually deserve. You know, it is possible for me to make a mistake when grading, right? So, so of course I will leave you this option to see your exam and to discuss the exam.
And if we do it in overleaf, right? Would the comments come in overleaf instead of Blackboard?
Yes, via overleaf, or you can via email. You can do it via email. But if you want like a discussion, we can even we can discuss this on Zoom. But usually, if you're not like content with the explanation that I am giving you for a problem via email, then we can have a chat. But anyway, we'll see about that. Let's see how it goes, and then. All right, I see some other questions here from Adib. No, I said tomorrow at 11:59, not tomorrow morning. There is no way I can give it tomorrow morning. And I will not make any special arrangements for anybody. Everybody will have the same setup for the exam. That's it. Yeah. And the code for LaTeX code will also be sent with the email when I send the test, just like Matthew said. Any other questions?
Yes, so on Overleaf, do you want us to put it in like a separate file from our homeworks and stuff, or?
Absolutely. The file for the homeworks will be separate. In fact, I will send some emails because after me sending you emails, it looks like some people don't understand. I want each homework to have a separate file, and I want the final exam to have a separate file. I don't want the final exam to be, I don't know, you overwrite it over some homework. No, it will be a separate file. I hope I make myself very clear. Well, the homework grades will be posted this weekend as well. I'm working on that. In fact, it is not my job to grade the homework, but I'm doing this extra job, which is pretty intense. I should have had a grader as well. Any other questions? The projects are due tomorrow. Yeah, tomorrow.
Midnight?
Yeah, at midnight. I will not accept any other project after that because it will be very hard for me to Yes, this review is recorded and this will be sent to you. Also the PDF file, so everything that we write and we discuss, and also the video. Absolutely, yeah. The project is optional. Everybody who typed their all 3 homework assignments on LaTeX via Overleaf will get those 10 extra %. Like I said, the project is optional, but the project, if you do it, you must do it via Overleaf. You must type it. Any other questions? You can also ask as well, not just write. But anyway, whatever you feel comfortable with. All right, guys. If there are no other questions, we can proceed. Okay, so like I said, the exam will be very, very nice. You'll love it. I'm sure those of you who really cared about this class and were like the challenge, the homework, especially the challenge that I put you through the homework assignments, I'm sure you'll love this exam. Like I said, the exam will be easier though. It's not gonna be like, even though it's a take home, it's 24 hours, but it will be easier. And before I do and talk about, like I said today, I said that I will emphasize more on our discussion in these 2 hours. I will emphasize more on the series of functions and power series. I want to do more examples with this because this will be relevant to the exam. But also, this does not imply that all the homework, all the exam problems will consist only with series and a series of functions and power series. So what I want you to, so the best thing, so the exam will cover the following. So it will cover differentiability, and here you can emphasize on, for example, the derivative, properties of derivatives. Mean value theorems. Here I will include as a special generalization of the mean value theorem of Lagrange's mean value, Taylor's mean value theorem. In fact, this will will be hand in hand with Taylor's series, and that we have discussed in class. And we spend a lot of time with this. In fact, a little bit too much time. And also, what's important here is also L'Hopital rule. And we have those two cases, infinity over infinity and 0 over 0. So that was the first chapter, and I spent a little bit too much on this because this was very, very important, especially for other chapters. Then we veered towards Riemann integral. And here we talked about properties of the integral. Okay, before we talked about that, we talked about Riemann sums. And integrability criteria. So we've seen when a function is Riemann integrable. We've seen also the criteria. You know, we've seen the definition. We also have seen Darboux criteria with the lower sum Darboux, upper sum Darboux, and we have seen that if they are very close to each other, then the function is Riemann integrable. Then we've seen also properties of the integral. Also, we've talked about continuity of integral. And here, we emphasized on the fundamental theorem of calculus. Fundamental theorem of calculus. And we've seen a bunch of stuff here. Also, we've talked about qualitative properties of the integral. Of the Riemann integral. And we've seen especially, I mean here, mean value theorems for integrals. Or or integral inequalities, and so on. And we'll also talk a bit about improper integrals, right? We've seen some examples. And then we veer towards, after we have done this, we veer towards sequences of functions. So this is another notion which is similar to sequences of real numbers, but this time we have sequences of functions. And here we've talked about many things. For example, we've talked about here about convergence. And when we talked about convergence, we're interested in pointwise and uniform convergence. Anyway, pointwise and uniform. And also we've talked about properties of sequences of functions with respect to, and when we talked about properties, we talked about continuity, differentiability, and so on. We talked about boundedness, when we can pass to the limit inside the integral, etc. Right? We've talked about this. We gave some criteria for uniform convergence and so on. So we talked about properties of sequences of functions, and in fact, when I say of sequences of functions, I mean about the convergence. So that was what we talked about. Then, in the same, so we correlated this with the previous chapter, previous two chapters. So if all the properties from the previous two chapters, from the differentiability and integrability, were understood, then there will be no problem with this too. And then we talked the last one, infinite series. And here, the infinite series, although I kind of disagree with the book here, because I don't like to talk, we talked about two things. So here, we talked about infinite series of real numbers. So series of real numbers, and here we talked about convergence. And here, and when I talk about here about the convergence, I only have two types of convergence. So pointwise convergence, like normal convergence, but I also have like absolute convergence. Absolute convergence. And we will see some examples. And also we talked about properties of series of real numbers. And when I talk about properties, I will talk about, I mean, of course, again, I will talk about convergence. So, and we've seen a bunch of criteria, and I told you there are many, many more. So we've talked about, for example, Cauchy condensation test. And in fact, I showed you an application of Cauchy condensation test. In fact, I haven't done it in detail. I left it to you as an exercise to show that the p harmonic sum, so the generalized harmonic sum, converges when the exponent is greater than 1 and diverges when it's less or equal than 1. Okay. And we've talked about also comparison test that you have learned. Presumably you've learned this in calculus too. Ratio test I told you, and so on. Anyway, we'll see more examples with this because I'll dwell more on this infinite series on the last 2 chapters because I feel we haven't done too many applications on this. So, and functions. And again, I'm interested in convergence. But this time, the convergence will be, I'll also have this word, uniform convergence. Just like in the case of series of sequences of functions, I have this word uniform here. And of course, also absolute convergence. But this absolute convergence is also, we'll find it also for and we've seen some properties of series of functions. Convergence again. So that's what we covered this semester. And of course, I gave you a criteria for, and we'll see more applications of this. Okay, so that's the material for this semester. Well, I would like to talk about the last 2 more. Yes. And I will start with some examples. So problems that we will solve, and I'll show you. But before we do this, I want to, in fact, no, I want to talk just a little bit about power series. So power series, because I feel like I haven't covered enough in class. I just said a few things about the definition and so on. So we said in class that these power series are a special type. So these are the special type, special case, let's say, of series of functions. And I want you to keep this in mind. And that special case is the following. So let's start with the definition. Let me recall the definition. And the definition, I will give it to you in a little. If you look at that, the definition is the following: a series of the form, and I'll call this in the following way. I will denote this by a function f of x equals the sum from n equals 0 to infinity. It's an infinite sum of an times x minus x naught to the power n, where an and greater than 0 are constants. So these are the what we call the coefficient of the power series, are constants. Is called a power series. It's called a power series in x minus x naught, right? So this is a power series of this form, this infinite sum. Usually, when when we talk about power series, usually it's centered around the point x not equals 0. So in the particular case, when, so remark, when x naught is 0, then the power series is given by f of x equals the sum from n equals 0 to infinity of an times x to the power n, right? So this is the power series. Okay, and we would like to talk about the convergence. So we're interested in convergence of this series, and so the question we want to answer is, when do we have convergence? That is the question. So we want to talk about convergence. And when we have convergence, I'm interested in what type of convergence do we have? Like, in fact, I'm interested in uniform convergence. So, and how to determine this kind of convergence? So when I talk about convergence here, I mean, what about uniform or absolute convergence? Or maybe, who knows, maybe they are the same. We'll see. Okay, so that is the question I want to answer. When does this converge? And if it does converge, maybe on what interval it will converge? And how do I determine the interval of convergence for such a series? And I will start with, maybe let me start with some innocent example. In fact, we've done this. So let me go back to that innocent example from that we did in class. So let's start with the example, and then we'll do more problems. All right, so the example that we did in class was when, so first one, when an equals 1. So when an equals 1, we have this function, f of x, is nothing else than just a geometric series. And remember, we did this in a, so this is a geometric series. Remember, we did this in two ways. And if you don't remember, I will ask you to go back to the notes from our last class, and also to the video. And you've seen that this will be convergent. And of course, this x is between, let's keep in mind that x is an absolute value less than 1. So therefore, in other words, this means that x is in the interval -1, 1. What do we know? We've seen that this the series does not converge uniformly on the entire interval -1, 1. We've seen that, right? But we have also seen the fact that the series converges uniformly on any closed and bounded interval, on any interval, let's say -r, with r between 0 and 1, right? 2, and we'll converge uniformly to this function, let's say 1 over 1 minus x. We've seen that, right? We've seen it 2 ways. We've seen it the hard way where we actually computed it. We've seen what happens, and another way was to use the Weierstrass Em Test, which you can go back to see how we did it. So, okay, I'm gonna say here, just use Weierstrass Em Test. To talk about uniform convergence, right? Let me remind you, and in fact, I will remind you the Weierstrass Em Test when we'll do more applications. So, okay, now I'm gonna give you the exact theorem before I wanted to start with some applications, but I want before I give you the exact theorem just to build some intuition, but I would rather go and give you the exact theorem. When do we have convergence? How we can determine the intervals of convergence, and so on. Okay, so the theorem that we have the following theorem, and I think I gave it to you, but anyway. So the main theorem is the following. I gave it, but anyway, I'm going to write it. So it says the following: let f of x be a power series. So again, I'm writing here power series, right? And suppose that I have a point. Suppose that I have a point. Let's say x naught is a real number, such that this series f of x naught, so at the point, which is nothing else than the sum, this sum, a n x naught to the n converges, right? Right? Just converges. I'm not talking about I'm not implying anything about the uniform convergence. So, okay. Great. Now we're going to do the following. So I stated it a bit different, but in the last class, but we pick any a, let's say any number a, such that a is positive, but it's less than x naught. Then we have that. Then we have that. Okay. We have the following. In fact, no, let me just stick with the notation so that just, let me pick R. So that we keep with the same notation as previously. On the interval, so on the interval, negative R, right? The series, the power series, the sum from n equals 0 to infinity of an x to the n converges uniformly. This is very important. So this happens. So we've seen that, in fact, it would be nice to do the proof, because we've seen, in fact, we've seen this through that geometric series example. But anyway, let's finish up the statement, and then on the interval, negative RR, closed interval, the series of the derivatives, the power series, the sum from n equals 0 to infinity of an times n x to the power n minus 1. So as you can see, I'm taking the derivative here. So this series will converge uniformly as well. Converges uniformly as well. And moreover, we can differentiate. We can differentiate term by term. Term by term. And in fact, we have following that f prime of x is nothing else than this, the sum of this series here. An times n to the power xn minus 1. Okay. This on all interval negative r. Wow. We have this amazing formula here, so I can differentiate term by term. I think I was asked by Michael last lecture when we can differentiate term by term. There we go. We have this, this is the answer. But now the question is, how do I find this R? What is this R? And if you look, how do I find, who is this R in fact? This R is nothing else than the radius of convergence. So we have the following theorem. So let me just state the following theorem, and then we'll do many applications. Theorem. And this theorem will concern radius of convergence. Anyway, let me just make a small comment about this theorem. We have proven this theorem for the example when an equals 1 last time in class for the geometric series. We've used the Weierstrass Em Test and so on. Anyway, if you want to go back, I will suggest you go back to that previous lecture. Now, the next theorem, which will determine how we can see if the series converges uniformly on what interval and so on, is the following. And in fact, I will, you will see that there is also will be an equivalent statement of this. So if I have a power series, so given a power series, and let me just take this to be centered around the origin, a power series, let's say f of x equals the sum from n equals 0 to infinity of an x to the n, right? So x not here, it's 0, so it will be centered around the origin. Let this R, okay, let me write it. And this will be 1 over, if you want, I'll put it like this. And here will be limit as n approaches infinity. It's in fact lim sub, but anyway, let's leave it like this, of the nth root of absolute value of an. So from now on, so and this will be a number which belongs to this interval. So I'm considering this number r. In fact, let me denote this by little r. So it's 1 over this. So again, if you have to compute the limit of the end root of this, and if the limit of this is infinity, then R is 0, and if the limit of this is 0, then R is infinity, right? So keep that in mind. All right. So this is R, and the theorem states the following. Then we have the following. 1. If R is positive, then the wait, let me. Okay, if R is positive, then okay, I should consider another R, which will be anyway. If R is positive, then the power series will converge uniformly, converges uniformly on the interval negative RR. So this is how we determine which interval converges uniformly to. So you take 1 over the limit of the end root of the coefficient of the constants, and then this is how you determine the interval of uniform convergence for the power series. Okay, for R positive, we'll converge uniformly on this. Then 2, if R is 0, then the series converges only at 0, at x equals 0 only. Okay, and then if R is infinity, right? We also have this case. It converges for any, then the series converges uniformly for any x real number. Okay, so that's the theorem I want you to keep in mind. In fact, this is the thing this is the formula. Probably you have seen this in calculus too. Okay, and now I want to do some examples. I will do, like I said, many examples. Let me start with the following example. So problems. Problem 1. So problem 1 says the following. In fact, I'll give you a couple of minutes to think of. Problem 1 says, suppose that f of x is the sum from n equals 1 to infinity this time of negative 1 to the power n over n times x to the power n. The question is, where does this series converge? And how it does converge? How does it converge? So we want to answer these 2 questions. Okay, I want you to look at it for a couple of minutes. I want to see, give me 1 second. I want to see if actually it's recording. Yeah, it's indeed, it's recording. Okay. I want you to look at it for a couple of minutes, and then we'll talk about it. Because there's a discussion that we need to make here. I think this problem is a very good prototype where we discuss everything. Everything is, all we have learned is put together into one problem. You see, there are two questions that need to be answered. Where does this series converge, and how it does converge? This is very important. So when I ask about how it does converge, well, you have to take into account what type of convergence do we have, like uniform, pointwise, so on. So think about it for 5 more minutes. Then we'll have a discussion. 2 more minutes. You see, X is a real number. So what did you get? I'm curious. So what do you think? Okay, time's up. Let's talk about it. So I want to see, how did you approach this? I'm very curious. So first of all, I want you to look inside the power series, right? We have this coefficient here. An is -1 to the power n times over n. Well, as n approaches infinity, you see, we must have some kind of a discussion here. So we also have x to the power n. And we know a bunch of things, and I told you that when I take, okay, let's see. If the absolute value of x is greater than 1, this is very, very important, this analysis, then what can you tell me about the limit as n approaches infinity of the coefficient? So of -1 to the power n over n times x to the n. Well, this will not be 0. I can tell you that. This will definitely not be 0. So therefore, for x strictly greater than 1, because x to the n will be much bigger than n at some point, right? For x in absolute value greater than 1. So as n is large enough. Right? So therefore, this limit will not be 0. So it cannot, this series, if this is different than 0, then this implies that the power series f of x equals, cannot even possibly converge. Cannot possibly converge. Right? So for this case, we're done. So the only we got this case out of the way. We cannot even have convergence. So we have to restrict ourselves. So this implies that we have to restrict ourselves. We have to restrict ourselves to what case? To the case when absolute value of x is less or equal than 1. That's the case we want to consider. See, it was a little bit tricky. Okay. In fact, you will see that we'll do it by hand, and then you will see that we can also employ the previous two theorems that I gave you, and the problem will follow easily. All right, so here we have this case when x is less or equal than 1 in absolute value. All right, great. That's great. And well, we have some cases here. So for this, possibly we have the following case. Let's say when x equals -1, you always look at the endpoints. When x is, so if, okay, let me put it like this so if x is -1, then our power series, it's just a constant series. So we'll have what? Can you tell me? So f of x will become what? Will become the sum from n equals 1 to infinity of -1 to the power n over n times, and here I'll have times -1 to the power n, which this will be -1 to the power n. This will be nothing else than just the sum from n equals 1 to infinity of 1 over n. What can you tell me about this? What is this? This is a series of real numbers, right? So this is a series, is nothing else than the harmonic series. What did we say about the harmonic series? What did we say? Is it convergent, divergent? I want you to tell me. I don't want to speak by myself. Help me out here. And I want Michael to shut up. Michael Killer, you're not allowed to talk. Somebody else. What did we say about this harmonic series? That it's what? I heard it's convergent. Did I hear right or I'm wrong? Come on, guys, say something. Please talk to me.
Is convergent.
Divergent.
Is what?
Divergent.
Divergent. Yes. Diverges. Divergent. We said this many, many times. Divergent. Great. So, but x equals -1. So I'll take this out of my interval of convergence. All right, great. So at this endpoint, I have this series. By the way, this is a series of real numbers. Series of real numbers. This is very important for you to know, to distinguish between the two. Like I said, we have series of real numbers, we have series of functions, and as a special case of series of functions, we have the power series, right? Keep that in mind. The series of real numbers will be just the constant term. When x is actually a constant, we'll obtain from the series of functions, or the power series, we'll obtain the series of real numbers. I hope I make myself very clear right here. All right, great. So at x equals -1, we do have some problems. So this series does indeed diverge. Okay, no problem. So we'll take -1 out of my interval of convergence. So we've seen that for x in absolute value larger than 1, everything just falls down, like nothing good happens in terms of convergence. So this series cannot possibly converge. Okay. Oh my God, series has a problem. Shut up. All right, and then we've seen that this endpoint at x equals -1, again, we do have problems. All right, great. Now, let's look at the other endpoint. What can you tell me? If x equals 1. What can you tell me here? I want you to tell me. What do you think is going to happen here? At x equals 1, what do we have? F of x will become what? Can you tell me? Will be the sum from n equals 1 to infinity of what? -1, again, a series of real numbers is -1 to the power n over n. Or if you want me to write it a bit nicely so that you can see it, -1 to the power n times 1 over n. What is this? This series. We've talked about this in lecture last week. What did we say about this series? What is this? It's an alternating series, and we've said that this series is what? Again, this is a series of real numbers. This is alternating series of real numbers. And what did we say about the convergence? Was it this convergent or divergent? What do you think?
Convergent.
This was convergent, right? How do we know? From Leibniz criteria, right? Convergent. Great. So maybe I should keep x equals 1 seems like a good guide to me. Okay. Now the question is, what else do we have left? The last case is what happens between these two numbers. So if x is between -1 and 1, so if x is in this open interval. And now, what can we do here? So let's look. Let's look. And maybe when I have this x in an interval, maybe I can use something that seems a little bit more familiar to you. And that familiar thing that we've talked about was what? We call it what? The Weierstrass Em Test. We want to use the Weierstrass Em Test. This is important. Remember, basically, let me just briefly mention it. The main ingredients for the Weierstrass Em Test were the following. So I have, okay, I'm not gonna be precise in statements. I have a sequence of functions. So this is a sequence of functions. And here I have a sequence of real numbers, let's say. So this is a sequence of real numbers. All right, great. And there is a relation, so let's put this like this. So this is the world, but there is actually a relation between these two. We know that there are two conditions met. The first one was that the absolute value of fn of x is less or equal than mn. So the sequence of real numbers, and of course, there's one condition here that I don't want to miss, is of non-negative reals, right? So the sequence of real numbers dominates the sequence of functions in absolute value. That's the first condition. And the second one was that the series associated to the sequence of real numbers. So this series, anyway, it doesn't matter. It can start from 0, from 1, converges. Converges. This is very, very important. Once we have these two conditions met, and I've said this many, many times, even at the office hours, in class and whatever, then guess what happens? Then after we can infer that the series associated, the series of functions, is uniformly convergent, is uniformly convergent. That's what the Weierstrass Em Test is all about. This is a very, very powerful tool. So now let's use it. So the question is now, let's see. So I have to consider, so like I said, we want to use this and we want to prove that our sequence of functions will satisfy the two conditions from the Weierstrass Em test, so that we can deduce that it's in fact uniformly convergent on this interval. So keep in mind we're here on -1, -1, 1, and let's see who Fn of x is what? Fn of x is what? Is -1 times n over n times x to the power n. And now let's take the absolute value, Fn of x, and this will be what? Will be the absolute value of times x to the n, right? And now we want to see that, okay, this will be the absolute value of x to the power n over n, and this will be very important. This is 1 over n times the absolute value of x to the n. But now since n is greater or equal than 1, this will be less or equal than the absolute value of x to the power n if you want, right? Okay, and keep in mind now that this guy, keep in mind, this is very important, it's between -1 and 1. And I want to show that the series of this from n equals 1 to infinity of x to the n, absolute value of x to the power n, converges when x is in -1, 1, right? And in fact, this is again the geometric series disguised for the, again, this is the geometric series. Disguised for the absolute value of x. So this is nothing else than just 1. So no, it's the absolute, because we start from 1, is the absolute value of x over 1 minus absolute value of x. And this will be less than infinity because we know that x is between -1 and 1. So by the Weierstrass Em test, these two conditions are met. So by the Weierstrass Em test, we know that this series, well, f of x, which is defined by this Fn of x, which is nothing else than just this. So it's -1 to the power n over n times x to the n, converges uniformly on -1, 1 open interval, right? So this is what we can say. So now, putting all this together, you can say that the interval of convergence, so the interval of convergence for the power series is given by -1, but open interval at -1 and 1, and we close it at 1, right? We close it at 1 because we've seen that at x equals 1 we did, and we have convergence. Okay. So this was the hard way of doing this. Well. So we answered the question. So let's go back. Go back. So the question, initial question, where does the series converge? We've answered. And how it does converge. We've seen that at x equals 1, it does converge. It's a series. But we've seen that for x in the open interval -1, 1, it does even converge uniformly, which is great. But okay, this is the hard way. You've seen we've analyzed everything. We've seen that for x equals greater than 1, something like this happens. But now the question is, you see, we have this theorem which tells you about the radius of convergence, which is given by this. And it says something here. You see, if this is the radius of convergence, if R is positive, then the power series will converge of -RR. But you see here, I have to check about the endpoints. So in other words, you can just do it directly. So the question is, what is the radius of convergence of our power series? So let me go back. So R, okay, little r was, right? Well, it's like I said, it's lim soup, but anyway, it's okay. We can leave the lim here. So this formula, so it's 1 over the limit, as n approaches infinity, of the end root of the absolute value of an. Okay. So in our case, an, keep in mind, is -1 to the power n over n, right? So this r will be nothing else than just 1 over the lim as n approaches infinity of, if you plug everything in, and at some point it's 1 over the n root of 1 over n, but this is nothing else. We'll just reduce to the limit as n approaches infinity as the n root of n. And by advanced calc 2, this is actually a homework problem that was supposed to be in any advanced calc 1, class, when we talked about the limits of sequences. This is 1, right? So fact the lim. You see, this is another approach, but you have to know what are the limits of the n root of n is 1. This goes back to advanced calc 1. Advanced calculus 1. That you're supposed to know. Okay. Right? So this means that according to the theorem, this means that this should be uniformly convergent on -1, 1. But we do have a problem at we have to evaluate the endpoints. So the endpoints will be when x equals 1. So we've seen that x equals 1 is good. We have that the power series is convergent. Is convergent. And at x equals -1, the power series is not convergent, is divergent. So putting all this together, so the interval of convergence will be usually it's negative RR. In our case, is -1, 1. So the interval of convergence would be is -1 and 1, closed interval. All right, I want to make a remark here because I gave you that the radius of convergence is the is 1 over the limit of the end root of the absolute value of n. But there is also another thing, another fact from that I will want to recall from advanced calc 1, and this should be like something very, very important. If I have a sequence of positive real numbers, right? Then we have the following amazing fact. The limit as n approaches infinity of the end root of an, anyway, I can have real numbers and I can just replace by the absolute value, but anyway, it doesn't matter, is the same as the limit of the ratio. An plus 1 over an, right? So that's another amazing fact. So it doesn't matter which limit you compute, it's the same thing. All right, now I want to give you, since let's go with the same thing with other 2 examples that I want to give you. So this was the first example. We've done it the hard way, where we analyze, we prove everything, and now let's do it easier. Problem 2. This would go very fast. In fact, suppose that f of x is the sum from n equals 1 to infinity of 1 over n factorial. The question is, where does this series converge? Where does the series converge? And how does it converge? How does it converge? Okay, I want you to look at it, and we can do this. I think this is like very standard. Well, I've done it also the hard way using Weierstrass Em Test, but these are very standard calculus 2 problems when you talk about the convergence of the power series, the interval of convergence, and you analyze the endpoints, and then you apply the root test or the ratio test. In fact, that's what I'm saying above here. It doesn't matter which limit you take. You can take the nth root of the sequence of the ratio of any 2 consecutive terms is the same thing. Okay, think about it for a couple of minutes. Let's say 5 minutes, and then I'll give you another example. So what do you think? Based on everything we've said, it's quite easy, right? AN is what? Is 1 over n factorial. Or in fact, yeah. In fact, let's put it like this. So by the ratio test, let's take the difference of, let's look at this guy here, right? So we have the following. So we have that the limit of this guy is x to the power n plus 1 over n plus 1 factorial over x to the n over n factorial. This will be nothing else than just what? Then the limit as n approaches infinity of x over n plus 1, which is 0. So therefore, since this is 0, we said that the series converges. So the series converges for all real x. Now let's see if the question is if the series converges uniformly, right? So suppose if x is, let's say, in between an bounded interval, let's say negative r. So this is quite easy to see. Then fn of x, which is, let's say, consider this to be, okay, x to the power n over n factorial, right? It will be less than this number a to the power n over n factorial. And now the question is this, the series of this, right? So this is my sequence mn. And now what about the series of this? Of mn is nothing else than just the sum from n equals 1 to infinity of a to the power n over n factorial. So this is a series again. This is a series of real numbers. Right? And I will leave it to you. In fact, it's quite easy to see that this is actually convergent. I'll leave it to you why. To explain why this is convergent. All right. So by the Weierstrass Em test, Weierstrass Em test, this implies that the series 1 over n factorial times x to the n is uniformly convergent, on any interval, let's say negative r, when x is in this interval. So it's uniformly convergent. Okay, so we've answered this question, and now let me give you another one. So in fact, this one, the problem 3 will be simpler. Yes, absolutely. I'm sending you, everybody will get the notes from, so somebody asked me, like, everything, everybody gets everything. It doesn't matter if you leave early and so on. Problem 3. Suppose that we have the following function f of x. This time I'm just gonna tweak it a bit. So this is the sum from n equals 1 to infinity of n factorial times x to the power n. The same question, where does it converge? Where does this series converge? And how does it converge? How does it converge? Okay, think about it. I'll give you a couple of minutes to think about it. It's kind of long, 2 hours, I know. And then after this, we'll do a problem which was given at the final exam at Harvard. And their intro to, oh no, at Berkeley, sorry. Yeah, Math 10 for Introduction to Analysis. So their class. We'll talk about an example. So you'll see some techniques alternating by taking the ratio, by taking the end root. So it depends. For example, in some cases, it's better to take the ratio because when you have factorials, you can just simplify them. But when you have some powers or roots, it's better to take the roots. So that's why I'm alternating the two techniques so that you see exactly where on what interval the power series converge, and moreover, what kind of convergence do we have? Okay, think about this problem. So, what do you have here? By the ratio test, what do you have? You have that the limb, as n approaches infinity, of n plus 1 factorial times x to the power n plus 1 over n factorial times x to the n. This is nothing else than just n plus 1 times x. And this is what is the limit of this? Can you tell me? When x is different than 0, this will clearly be infinity. Anyway, infinity if x is different than 0, right? If x is 0, in fact, we'll have 0. So this series, so our series converges only for x equals 0. That's it. Okay, that was the problem. Now, I want to do one more problem. So problem 4. This was Berkeley, UC Berkeley. Math 104 final exam. So there, Math 104 is called Introduction to Analysis. So this is the Introduction to Analysis course. That's what we have as well. So it's the equivalent of our class. All right, so we have this, and the problem says the following. Consider the power series. So consider the power series and the power series, let's say, is given in this way, is a sum from n equals 1 to infinity of 2x, everything to the power n squared, pay attention, everything over n. And it says the following. I'm going to give you just like it is. In fact, this is a very nice problem. It's a very nice problem, actually, yeah. They could have made it a bit easier, but anyway. Show that the series diverges at x equals 1/2 and it converges at x equals -1/2. So we have to be a little bit careful here. And part B says the following. What is the radius? What is the radius of convergence? The radius of convergence of the series. Either calculated explicitly or justify carefully using part A, or justify carefully using part A. You see, that's actually, it's very nice. It's a great, the problem is phrased great, using part A. Okay, imagine you have something like this in the, okay, think about it. I'm gonna give you like 10 minutes to think about it, and then we will talk. We'll discuss it. So you should be very, very careful. We've talked about this. We've seen something similar earlier. I know I'm giving you only 10 minutes, but at least just some ideas. This could be like this is a very nice problem, exam problem, very nice. In fact, I was almost on the verge of putting this in the exam. So I was deciding between this and another problem. And eventually I chose the other problem. I said, let's not exaggerate. Although it doesn't matter if it was a Berkeley problem, I do not consider you in any way inferior to other schools. So for me, it doesn't matter which school, what exams, where are they from. So you should be able to do these exam problems, even if they come from Harvard, Princeton, Berkeley, whatever. I don't care. So. It just requires a little bit of a discussion because I have there the n squared. So you see, part B is very bit, I wouldn't say tricky. It says it gives you an option. Either calculate it or explicitly. So you either know how to compute it explicitly or justify carefully using part A. So in other words, this is just a combination of the two theorems. Okay, let me go back. Of the two theorems that they're here, you see? There are two theorems which say the following. Theorem which tells you exactly on what interval this converges uniformly. And then the second one, it tells you exactly how to compute the radius of convergence. So, okay, let me give you 3 more minutes. I'll be right back. Okay, let's see. Let's discuss this. Oops. What? Okay, let's talk about it. Oh my. Okay, let's see. So let's analyze it. You see, you can do this by hand, but you can also just use the theory. So let's. What about part A? What can you tell me at x equals 1/2? What do you think is going to happen for x equals 1/2? What do you think is going to happen to the series? So if we put into our series x equals 1/2, our series will become what? Two x to the power n squared, everything over n will become nothing else than just what? Can you tell me? What is this?
1 to the n squared over n.
1 over n. You put there x equals 1/2. It will 2 times 1/2 is 1. And what do we know about this? What is this? We've said this previously. How do we call this?
The harmonic series.
Harmonic series. So we know that this is divergent. So divergence. So this is the harmonic series. All right, great. For x equals 1/2, the situation is not good. But now, and this will diverge to infinity. But now let's see for x equals -1/2. And here we should be a little bit careful. So we have that our series will become the sum. This will be nothing else than just, well, we should be very, very careful here. So it will be -1 to the power n squared, pay attention, over n, right? We have to analyze. What do you think of this series? Is this convergent or divergent? Well, let's see two cases. So n is even. Divergent. Let's analyze. When n is even, it follows that n squared is even, right? So in other words, and also when n is odd, one can prove that n is also odd, right? So this means that, exactly. So this means that -1 to the power n squared is nothing else than just -1 to the power n. So we have that this series will be nothing else than just exactly this series, which will converge. So this is the alternating series. So this is this converges. So this is what we call the alternating series, and we've talked about this previously. Okay, great. So we have that this guy is good. So this guy is good at x equals -1/2, right? So we do have convergence. All right. Okay. Okay. Now you can use part A for this, and I'll leave it to you as a homework since we don't have too much time. I'll just do it directly. So the radius of convergence this will be nothing. Also, the radius of convergence will be nothing else. So let's say R is 1 over lim. It's like I said, it's in fact lim sub, but anyway, let's just write it like this. The absolute value of an, when in our case an is 2 to the power n squared over n. So in other words, this will be, and in fact we should be a little bit careful here. So an, where in our case, an is nothing else than just is 2 to the n, right? Because we have 2 there inside, is 2 to the n times n to the power negative 1/2, right? Because, yeah, pay attention, if n is a square, square number, and 0 otherwise, right? This is who an is. And now we just have to compute the limit of this. So the limit of this, if we take the square, so this will be nothing else than at some point we'll have the lim as n approaches infinity. If we put everything together, so if we want to take the limit of an in absolute value, everything to the power 1 over n, this will be nothing else than just, if you want to put their lim as n approaches infinity of, because we said that this is a square number, we have this is a sub n squared, everything to the power 1 over n squared, and we know that this is 2 to the n. So this will be equal to the limit. So here I go back to advanced calc 1, as n approaches infinity of what do we have here? So we know that an, we just replace, we know that an is this guy here, right? So this would be 2 to the power n squared over n, everything to the power 1 over n squared. Oh my. And this will be nothing else than just 2. We'll take the 2 out. So this will be the limit as n approaches infinity of, what do we have there? The absolute value of n, everything to the power negative 1 over n squared. Or if you want, this guy, and now we have to compute the limit of this. And we have to go back to advanced calc 1. And here is the trick. So the trick is the following. So this absolute value, so I'm going to use the squeeze theorem. Indeed, the problem that I put in the exam will be way easier than this. So the absolute value of n to the power negative 1 over n squared is greater or equal than, so it's less or equal than 1. That's obvious, right? And is greater or equal than the absolute value of n to the power negative 1 over n. And then everything boils down to what is the limit of this. And we have previously seen that the limit of this is 1. 1 converges to 1 as n approaches infinity. So by the squeeze theorem, this will converge to 1. So this limit will be nothing else than 2 times 1, which is 2. Right? Here I use the fact again, goes back to the fact that the limit as n approaches infinity of the n root of n is 1. Keep that in mind. Okay. And here I use the squeeze theorem. So the radius of convergence will be nothing else than 1/2. That's the radius of convergence. So it will converge on the interval for all the values which are in absolute value, all the values x which are in absolute value less than the radius of convergence, which is 1/2. So it will converge on the interval negative 1/2, 1/2, right? We can say this. So, but we have seen that our series does not converge at 1/2. So it will converge only on the interval negative 1/2, closed, open 1/2. That's it. And that's the theorem. That's the problem. Anyway, how do you find this problem? Was it difficult or was it? What do you think? This last problem.
Oh,
Was it
I mean, it was a little bit tricky, but
a little bit, right? With the square thing, with the even, with the odd,
exactly with the square power, it was a little bit tricky. But
other
it
than
makes
that, it was
sense. It makes sense.
okay. You see, these are the type of problems that where you can learn something from. So anyway, this was given at the math, was an exam problem. In fact, I looked at the exam right now, math 104. I think this was given, I don't remember what year. Let me see. They don't say. What year is it? Anyway, but from what I've seen, they use the same exam at Harvard as well. Wow. And their intro to analysis course. Anyway, this was the province of beauty. I would like you to go over everything we've talked about today. You'll have the video as well. I'll send it to you, and then you'll have what to look for. And definitely this will be helpful for your exam. Well, ladies and gentlemen, I would like to thank you very, very much for a wonderful semester. I hope you have enjoyed the class and also the review sessions and also our interaction as much as I did. I wish you all the best wherever you want to go. You go into industry, you want to go to pursue an academic career, such as, I don't know, go for a PhD or a master's degree or whatever, graduate school. And feel free to ask me for any advice, and if you want to pursue something. All right, thank you very much. God bless you all, and we should wait for my exam tomorrow night. Okay, thank you very much.
Thank you, Cezar.
Thank you.
Thank you for
Okay.
everything.
Thank you.
For your extra credit opportunities, mostly.
Yeah.
Thank you.
Thank you.
Okay, bye-bye, guys. Yeah, have a good one.
Bye.
Is it-